welcoming to the stage Jamie Thomas.
Thank you. Thank you. Okay, let's see if I pass the test. Is this on? Okay. Well, great. It's great to see the NC State students, faculty, some IBMers I recognize, some retired IBMers, Fidelity. So thanks for coming on what is not a great weather night, by the way. So, you know, some days I wake up and I wonder, how did someone with a computer science background end up running all the hardware in IBM? So it just goes to show you can never chart your destiny. You never can quite know where your career might lead. There's many things that you can do with the kind of disciplines that you all are majoring in, so congratulations on the choice. Tonight we're going to try to demystify quantum a little bit. I would warn you, I am not the quantum physics person creating the semiconductor, so I'll take it from my perspective, but my team is driving this initiative, and truly this is one of the most exciting startup initiatives that I have seen in my IBM career. And a little bit about me, we've already said I'm a computer science major, and it's great to see all these ladies out here, by the way. Not enough ladies going into engineering and computer science, so we need to boost the lady content rate in these fields, so it's one of my passions. Is quantum computing important? So that's the first item on the agenda. And if we think about this picture, some of you are way too young to even recognize what this is, right? Doesn't look anything like the iPhone, but of course it is the ENIAC computer from 1946. And this computer was very important for the U.S. Army at that time for ballistics testing. It actually was very functional and effective for about 10 years. And you can see the computers, the human computers here, like the ladies that were featured in the Hidden Figures movie, if you saw that, right? That's how we got the name, went from human computers to real computers. But this was a state of the art at the time. And many folks believed that there would only be an opportunity for about 5 of these machines because we didn't envision the art of the possible at that time. And of course, these machines started early on to start to really make an impact in our everyday lives, from powering the Social Security implementation to helping us understand how we put the man on the moon through the work that we did at NASA, and then charting the journey to the moon, as well as running all of our financial institutions in short order, as well as partnerships like we did with American Airlines to build the world's reservation system for airlines, which, by the way, is still in use today. So when we IBM think about this journey to quantum, we think about it from the perspective of what happened here. And we think big. We think that this really will have a profound impact on the world, on industry, and we have to think about how we build the skills and build the commercial use of this to really take advantage of it. Because it was those partnerships that were done with NASA, with folks like American Airlines, that really made a difference with the uptake of the original technology that looks so antiquated today. So when we look at the opportunity and what is forecasted around the world for quantum, you see that there is an arms race. There's an arms race across geographies, across governments, to obviously fund what they think is the state-of-the-art platform for the good of their environment, for the good of their country, their geography. We see this in Europe. We see it in the U.S., where Congress has passed a quantum initiative and committed to spend a certain amount of money over a period of time, thanks to NC State. Dennis, I think you were there with us at Congress. We took the quantum chandelier there to explain it to the senators. There's lots of tweets out there with the senators taking pictures with the chandelier, if you want to go peruse that. But it says it's an important initiative. There's different views on how big the market will be by when, but suffice it to say, we believe it will be quite large, and it will have the power to solve very unique problems, which I'll talk a little bit more about. This is an interesting picture, 1981, when IBM and MIT got together, and a lot of the most famous folks that influenced quantum are in this picture. From Richard Feynman, who won the 1965 Nobel Prize for Physics, considered one of the premier physics folks in the world ever, and his implications on what he did for quantum, to Charlie Bennett, who is in here. He's known as the father of quantum information science. He is an IBMer, and he is still working at IBM. It's amazing. And so IBM has a long heritage with quantum and investing in the quantum theory well before we had a product. And of course, Peter Shor, famous for Shor's algorithm, the guy that set us all crazy about cryptology and post-quantum cryptology. In fact, a lot of times we have meetings on quantum. I'll have lots of financial institutions come and only want to talk about what's going to happen to cryptology. Forget material science and all this other stuff. What is the impact on security? So this says that quantum has been on a journey for some time. If you look at this timeline, IBM has been involved throughout this journey. Oddly enough, we're not the blue dots on this chart, we're the white dots. I don't know why my design team was so challenged, but we picked the wrong color. I realized this week. But at any rate, if you look at this, you see this thing called the Epr Paradox. Well, that's Mr. Einstein weighing in on this topic early on when he was at Princeton with two other scientists saying, there's this spooky concept out there, around this quantum theory that he didn't know, we didn't quite understand it in the same way we do today, but spooky motion from a distance, right? How do these things have this effect on each other from so far away? It's what we now call and know as quantum entanglement, which we'll talk a little bit more about, but back then they didn't have that terminology. So a long road to get to where we are, where we can see today that quantum is and will be a product and will have impact on commercial industries. So are all the classical computers dead? Are we going to just restart with quantum? What does this really mean for all of us? So I brought along a picture because we'd like to brag a little bit. This is the state of the art in supercomputing today in the world. This is the IBM developed Summit computer, which just won #1 in the world as the world's top supercomputer, and it is resident at Oak Ridge National Laboratory in Tennessee. And I have to thank them because they paid for my college tuition. I was an intern student there. I was doing uranium enrichment. We won't say more about that. But at any rate, this is the world's largest supercomputer. And this thing is 200 petaflops of capacity, 200, with a huge amount of storage, 250 petabytes of storage. But it is the state of the art in the world today, right, from a classical computer perspective. So we'll keep this in mind as we go forward, because now we're going to talk about, well, if that is state of the art, why do we need this thing called quantum? Well, in fact, there are problems that we can clearly identify where we cannot solve with these classical computers. Or in fact, you could solve them, but it takes too long. If I'm in financial markets and I run past a certain window, the information that I've found now is no longer valid because the time for utilization of that information is now past. But of course, one of the most interesting logistics problems is traveling salesperson. And we don't really have these people that show up at our door today, but there's still a thought process, and even those that call us on our cell phones, like many people did to me today, that I did not want to talk to, by the way. But there's this notion that you can compute with a classical computer, maybe 50 different variations of this thing, but by the time you get to 1,000, the permutations that you have to worry about are mind-boggling. Now, I spend a lot of time at the airport, so I am particularly interested in how this might apply to airports, right? So think about when there is a Hurricane Florence and you're American Airlines, and you suddenly have to reschedule everything based on the weather data that you're getting, every 5 minutes literally. You have to reschedule all those flight crews, the logistics of the plane. It's just a humongous challenge that can change very rapidly and is almost not computable in the right amount of time. There's many logistics problems like that, right, that we can relate to in real life that are sincere challenges. In fact, I can tell you that the people at IBM that work at the weather company, they are best friends with airlines, right, because those airlines are constantly getting that data feed. And Stacy, you know this, you work on Watson, right? She works on Watson. We understand that it's real-time information as compared to what it used to be in the past. So another problem, molecular modeling, right? So we all like to consume this molecule called caffeine, but in reality, caffeine is reasonably complex when it comes to the world of molecular modeling. It's much more complex than things like aspirin, which are very common from a pharmaceutical perspective. The number of molecules here makes it more complex because every molecule has a certain number of circumnavigating electrons, and it adds, a 2 to the n factor in the complexity of having to model something like this. So we believe that to effectively model this, it's 10 to the 48. So our supercomputer that we looked at before doesn't have the capacity to model this molecule because it doesn't have that capacity. In fact, it would take 1,000 billion of those Summit computers to actually do the modeling that's required for this. It's mind-blowing. So it's an exponential problem is what it is. It's an exponential problem that a classical computer would have trouble computing. So this brings us to quantum and some of the basic principles of quantum, and that quantum is founded on something called the qubit. So unlike the principles of computing today where you have your bit is either a state or a 0 or 1, these qubits can be a 0, 1 at the same time. Or they can sort of be stuck halfway in between in an odd state. But that gives us a much larger landscape, if you will, in terms of what we can reach. And the interesting thing is back to that Einstein theory, the spooky theory, right? Is that these things can become entangled if you have the right system. And it's this entanglement that actually adds the value and brings the quantum mechanics aspect of this into the computer and allows us to compute things that we believe were not possible before. And with the right application, the right answers are amplified and the wrong answers are de-amplified in this scheme. But it's this entanglement that allows us to compute things more quickly and across a number of different dimensions. So we got the qubits, we've got the superposition, and we've got this entanglement notion that allows us to really do something very different. And you have to take a little bit leap of faith. I think one of the examples that we've used many times, and you may have heard this, is say I'm playing with cards, right? There's 4 cards, and I want to find the queen in the cards. I'm a great, a poker player. I'm not really a poker player, but I'll pretend for now. And the reality is in a normal set of cards, you're going to go through this so many times before you find that queen. However, with a quantum computation, you're going to find the queen the first time, every time, because of the way it works. So this gets back to the scale of the computer. The qubits allow us to scale with each qubit 2 to the n. So think about the power now. IBM, we have 4 different models of this computer at this point. We have a 5-qubit model, a 16-qubit model, a 20-qubit model, and we are working on the 50-qubit model, which has already been prototyped and proven. So we get a huge amount of capacity with this 2 to the 50th qubit. But it's not just about the qubits. You also have to have effective error correction in the fundamentals of this machine, because we could have a lot of qubits, but we could have such a poor error correction dimension that we actually don't get the results that we need. So it's the 2 of these factors together, the number of qubits, the error correction, that creates the value of the machine, and we in IBM call that quantum volume. We actually think that quantum volume is more important than the number of qubits because you combine the qubits with the error correction factor. And each generation of our machines, we're getting the error correction rates improved as well. To put it in perspective, 2 to the 300 are more atoms than in the universe. So when we think about computers that are 2 to the 100 qubit, we start to get immensely powerful machines in terms of what we can do. So we believe that these classical computers will endure forever because, in fact, they're quite great at processing transactions and also processing large sets of data. quantum computer is not a data processing hog, if I could say it that way, right? What it can do, though, is start to train models more effectively so that we can intelligently apply that model information against the data set. And so we see the quantum computer as being an example of an accelerator. So today, in a lot of the engineering technologies and deployments in Summit, the supercomputer, there's over 9,000 of our Power 9 processors married up with over 20,000 NVIDIA GPU accelerators, accelerating that workload, making it the largest artificial intelligence computer in the world. But what really happens with quantum is quantum becomes a next generation of accelerator, where you would partner your traditional system with this accelerator utilizing a very different technology. So what kind of problems can we solve? And these are pretty exciting problems. Obviously, the one that's very obvious, given the discussion, hopefully, is this whole area of chemical materials and molecular modeling. This affects everything that we know today. So I always like to think about that story that we all heard, I think it was maybe a year or two ago, my years run together, about the cell phones that caught on fire. What is that? That is a complex material science issue. Trust me, we have a new mainframe we're developing. We're putting lithium batteries in there. I don't want my mainframes catching on fire. So we have material scientists working on this. The material science and industrial engineering for complex machines is very, very complex. Understanding what alternatives there might be for electric batteries. Understanding the life management of electrical batteries, which affect everything in the world right now, all the manufacturing sites, automobiles, everything we think about. This is a really important and very expensive topic right now. We know that we're constrained on raw materials for some of these things, right? Pharmaceutical research. So many drugs are developed that never actually make the trials. So how can we improve the simulation of these things such that we actually do better before we get to the trials? Simulation and all of those kind of advanced logistics technologies are actually a part of this equation as well. Artificial intelligence, I talked about the ability to create better models faster, right? Because models could be ephemeral in terms of their value, depending on the amount of information that you need to consume and the validity of that information over time. You may need the ability to create and train these models more frequently, as well as optimization problems, right? So if I have a portfolio of optimization, how fast am I able to do that? I've been on Wall Street before one time, and I always ask people questions I read about in the Wall Street Journal. And I asked one of the gentlemen at one of the banks what was going on with the derivative pricing. And it was one of these periods of time where the Chinese currency was fluctuating so much. And the fluctuation of that currency had such a profound impact on the pricing, their pricing algorithms cannot complete in the right amount of time, right? So there are certain things that have a long tail, right? If you're able to reduce the long tail, you actually improve the risk analytics or the ability to do things that you cannot do before. There's a huge application of some of this in risk management, fraud detection, and other elements of financial services industries. So these are the key areas we think will affect first. It does not mean these are the only areas, but we think these will be the primary areas to start with. Pretty exciting stuff. Material science is big, by the way. This can affect things like exploration of oil, fluid dynamics in all industries, CFDs. It's a very lucrative front, if you will. So what are we doing to commercialize this thing? We think there's an opportunity here, but these are some pictures of our machine. We have traveled around the world with the chandelier. So the chandelier is what many people see. That is actually the interior of the dilution refrigerator or the cryogenics unit. And so the processor, which is semiconductor transmon technology, when you look at it, it looks a little bit like one of our processor from just looking at it today, but of course it's very different underneath the hood. But that processor is sitting in the middle of that dilution refrigerator that's running at a temperature that's colder than outer space, 15 millikelvin. Because we're speaking to the processor with microwave technology. And it's these microwaves that you have to get right in terms of the pulses to actually sustain a processing unit with the processor so that you can get some value out of it. That is the tricky part of this. And if we don't keep it very cold, then we get too much interference and noise from around it that really impedes our ability to process. So driving the dilution refrigerator is an electronics unit, and that somewhat looks like a rack of electronics today. That's an old picture there. We're in our 4th generation of electronics because our first set of electronics, as you can see from this picture, looked a little bit like the ENIAC. And it had so many wires coming out of it that everybody said, stay away from it, don't touch it, right? Because if you pulled a wire out, you might have a problem. So we had to re-engineer the electronics, understand how we can manage electronics. Because the computer is running in a cloud model, we do need to be able to scale in a data center for successive electronic units and, of course, for higher qubit rates. Also, I would tell you that we don't charge this way today, but the price per qubit was not sustainable. I have to manage cost for hardware because for some reason clients don't want to pay $5 million for every box, right? So we're always very cost focused so that we can get a better price. And we were not on a scalable model with the electronics we had, so we've had to work on that a little bit. And then, of course, the processor technology itself, which is very the secret sauce. And of course, there's a lot of different opinions about what the right technology will be. We believe that our technology will allow us to create a universal computer that can solve many problems as opposed to be just tailored for a narrow set of problems, and that's what we're really focused on. A lot of fun here on this front because you've got the electronics moving at the same time, the dilution refrigerator is changing, and the processor is changing. So a funny story, we have a team that runs between the systems unit and IBM Research. We're one team. And we have experts on the team, people that are PhDs in physics, experts in mechanical engineering, electrical engineering, software experts with quantum physics experts. And so when we first started this journey about 2 years ago, we had to start meeting together. And so my team told me, we have created an agile Scrum approach to this. We have an agile meeting. And they said the physicists, the quantum physics people show up to the meeting. And I told them, I said, oh, you've trained them on Agile. And they said, no, we just told them to show up for this meeting once a week for 30 minutes. So we're not quite sure that the quantum physics people still understand they're part of an Agile process, but this is working. It is really working. It's funny to work with research. I have fun stories. So a little bit more about this. We started this as a cloud experience in 2016. And at that time, we gave everyone, and we still have free access to quantum in the cloud. It can only be accessed in the cloud because you notice it's a very different form factor. Client data centers are not ready to consume this and pipe helium into their facilities, right? So we started this on the cloud. And it was the right thing to do because today we have a huge number of folks working with us on the cloud using our 5-qubit and our 16-qubit algorithms. And we call this quantum experience. It has had enormous adoption. We've gone over 100,000 users of the quantum toolkit. You can see here that we have 6 million experiments. We really track closely papers that are meaningful. Papers that perhaps some of you could write. We track that as a critical indicator of the traction we're getting around skills and understanding of quantum. Our goal is to create commercial value out of this. Without our partnerships, like with NC State, without ability to train individuals, we will not understand how to get value from it. Once again, we're thinking back to the early days of the ENIAC. How many people understood how to interface and use the ENIAC? Not many in the beginning. We had to build those skills, right? We had to build the skills that allowed us to realize value from modern computing. Most important is that we have a hardware innovation, but we have to have software innovation. And so this is exciting for me as a computer science major because we're building an entire new software stack here. At the bottom of this stack is something that we started with called Quasm. Quasm language, you can think of it as the simile language for quantum computing. When I started at IBM, I worked on mainframes, so I had to be an expert in assembler language, right? Could tune all the bells and whistles. Well, at this lower level, something called Qiskit, our toolkit is called Qiskit because it's Quantum Information Science Kit. We're not allowed to put a U in there, which makes sense to some of us, but no, that's not appropriate for quantum physics people. So it's Qiskit. And Qiskit has a layer here called Terra, which is really the fundamentals of how you control the quantum gates. So this would be used by researchers who really want to tune the computer at a different level. But that's appropriate because we need to have APIs at all layers of the stack here. And then we have Qiskit Aqua, which is really about those algorithms. And once again, that starts to be about creating the commercial value, creating algorithms that could apply to chemistry, to financial services. And with Aqua, because we in IBM do have a fundamentally strong understanding of chemistry, and chemistry is easier in some ways to adopt common algorithms to something like this, we've implemented a set of capabilities that allow us to capture Gaussian chemistry algorithms more easily and run the existing algorithms on the quantum computer. For the clients that we have shared this with, they have been fairly amazed at the ability to take some of the things they use with classical environments, but then start to take advantage of the quantum capabilities through what we've done here with Qiskit Aqua. And of course, this is water and earth, and for those of you that follow the meaning behind Aqua and Terra. But this is very important, the whole notion of a toolkit that everyone can use as appropriate for what they're doing, whether they're algorithm writers, whether they're controlling quantum gates because they're physics researchers. And of course, most fundamentally, coming into Qiskit at the top, you can access it through common languages like Python. So you do not have to learn a new programming language to access these APIs, which is a fundamental aspect of our journey to reach more and more developers so that it's easy for them to access it. So we've been on a constant ramp. We track our utilization closely in terms of consumption of our toolkits. We also track, by the way, Dennis, our member hubs and who's accessing it. We have a utilization chart that shows who out of the hubs who's using the most capacity on any given week in the cloud, just to see what's happening out there. We don't share that though too much. And of course, in 2000, we announced that we didn't have strong intentions to build a leading commercial computer, universal quantum computer, because one that would actually be able to solve problems across these different industries. So that's the journey we're on. We've committed to deliver the 50-qubit computer. We have prototype, we have it running, and so it is a very serious endeavor for us. We do consider this a significant to IBM as the invention of the first mainframe, and you all are way too young, but of course that was the biggest bet that IBM had made at that time for the IBM company. A huge industrial bet and one of the biggest that was ever made in industry to create that machine. So that is our mindset as we continue this journey. So we're building a network, and NC State, as I said, is an important part of the network because we have to increase the aperture of trained researchers, folks that can take us on this journey. So that's a part of the network hubs that we've created around the world to help us do that. We also have outreach to startups. So we have a startup program, and we have a large ambassador program that we've embarked on. And we have a few of the IBM ambassadors over here on the right that have come to join us today. Our network looks like this today. So you can say we've logically picked universities around the world. We have Keio University in Japan, a rich area for materials science given the industrial nature of Japan. Oxford University, Oak Ridge National Laboratory is a quantum hub. University of Melbourne in Australia, NC State, as we said, in North America, Bundeswehr in Germany. In addition, we have partners that have announced with us. We have commercial partners who have not announced. These are the ones that have chosen to announce their participation. You see JPMC is obviously financial services. Samsung, Daimler, JSR are more focused on material science. They're industrial organizations. And then you see our education partner. We're still working with MIT after all these decades. We'll have other education partners as part of those hubs. We have some academic partners, and then others have different membership as opposed to the partners. And then, of course, the startups that are important for us. Because when you're so early in this kind of endeavor, you know that you'll need lots of firms to provide an ecosystem around your machine, your software stack, and this will be very much evolving over time. There's the NC State announcement that we made, which was really outstanding. I was really proud to see NC State, being from this area, be first to do this in North America. I think it's a really big statement for the university, and also being at the forefront of new technology like this. So it was really good. And the last things that I would say is that this is a journey that's just started. We believe that this will be a journey for the next decades, but we will start to get value out of these machines. Given the arms race that occurs in the IT industry these days, the competition will force more focus on this than maybe there was, of course, decades ago. It's a different world today. And so that's the way we look at it. We have an ability here for you all to go out and explore the resources to become users of Qiskit, to become people that can experiment out there with these programming APIs, help us write papers, and help us learn more about this. And of course, we're very engaged. We have a team that's called QStart that actually is dedicated to working with our hubs and working with our commercial partners to, once again, we believe that we can create the next airline reservation system. It won't be the airline reservation system, but hopefully it'll be solving a big problem. Or we can help take the man to the moon. Be a different problem, right? But we could be a substantially large problem that could have a big impact, positive impact, hopefully, on all of us. So that is a little bit of our story. Does it make sense? I did not talk about Schrodinger's cat, who's maybe alive and maybe not alive. That one hurts my head a little bit. I do like cats. But makes sense? Are there any burning questions that we want to ask?
So if there are questions, where are my ambassadors? They're coming. Okay. So while my ambassadors are coming, I'll just say if you have a question, you'll raise your hand. If you will, just wait until you get the microphone to ask your question. That way we can capture it on video. Who has a question?
Hello, thanks for speaking. So there's been a lot of talk about quantum computers kind of destroying cryptography.
Yeah.
So could you explain to a computer science undergrad, like that's the audience, why that may or may not be true?
Right. So we definitely believe that over time that a quantum computer will be able to break the existing cryptology algorithms. There is a debate on how fast that will occur. My team personally does not believe it's, on the near-term horizon, it's a little bit out there. However, all vendors, including IBM, are very much already working on post-quantum cryptology. And what that means is we're working with the standard bodies to implement cryptology that can be implemented against data that's created today such that when the quantum computer becomes a reality, the data will be safe. So in the same research organization that's creating the quantum computer, right down the hall is the team that's creating post-quantum cryptology. And so that is the cryptology that we hope to deploy sooner than later, because the goal would be to encrypt that data with a new algorithm that the quantum computer cannot penetrate. So that is a very important topic, and one that we're certainly investing in. And there's standards bodies like NIST that are very active in this whole arena.
You mentioned that the quantum computers were sensitive to interference. How hard is it to check that they're still working right? Sorry if that's a stupid question. Is there some simple test program you have, or is it a long and complicated process to check that they've been working under proper conditions?
Yeah, no, we do have methodology to understand. What we look at is the coherence of the processor and the time for the coherence. And so we actually have to do that every time we come out with another generation of this machine. And we're on the fourth generation, from a 5 to 16 to 20 to 50 qubit. It has to do with the noise considerations of the system, and also the fidelity of the error correction, right? Because if it becomes too noisy, we get no value out of it. And so every time that electronics panel is changing, the semiconductor is changing, there's opportunity for this to go awry. And so we're very much checking that, because as I said, our goal is improving this quantum volume characteristic, which is the combination of those qubits with this error correction noise reduction factor. So we absolutely have the ability to do that. And not only that, that original electronics unit was not the most manageable beast on planet Earth, right? So we have implemented these new electronics hardware, something simple, hardware management consoles and state-of-the-art management capabilities that allow us to do a lot more, and that's going to be very important for what you're talking about.
So my question is, will quantum computers will have an impact on blockchain?
Well, they have effect on blockchain. Well, that's a very good question. What I think they will fundamentally have an impact on is logistics, right? So I own supply chain for IBM. So I think one of the most fundamental advantages of blockchain could have is on supply chains. Because I can tell you, my supply chain, my shipping agent, which is not me, has actually lost a mainframe before, which is not a good thing, at the airport. We find them eventually. They're pretty heavy. They're 2,000 pounds, so you can't run away with one quickly. But, I'm putting tracking technology on them for that reason. But blockchain, will enable us to have tracking. It's the challenges for like a GPS technology, a lot of them aren't allowed on airplanes. We have to ship these things on airplanes and stuff like that, right? But blockchain has traceability of your whole part supply, right? So to the degree that a quantum could help with logistics, by theory it would also maybe improve some aspects of blockchain, but that's something we have to, think about. One of the things I noticed is that Amazon announced its East Coast logistics operation in Nashville. I know for a fact that, having gone to University of Tennessee recently, they have a big supply chain institute, logistics institute. We hire people from there. These logistics problems and everything are very, very tough, particularly in a world where everybody's shipping everything. You cannot believe it. Our supercomputer last year, we had a sad thing happen. We were trying to ship a huge amount of stuff out of Mexico. And guess what happens? It snows on the border of Mexico and Texas. Well, you can't get any trucks to move, right? But we felt we were safe. We had an airplane, 747. Fly it down there, pick all the stuff up. Airplane had a parts failure. There were no free 747s in the end of last year. Why? Because all of you are ordering your cat litter to be delivered, or your toilet paper, right? So I can't move my computer. So I did eventually find a cargo plane, but let me tell you, it's not anything to be taken lightly in a world where the capacity is just crazy. It's crazy, right? Logistics are extremely complex, and I think there's going to be some opportunity for these things to come together. I don't know what that is right now. Huge fan of blockchain for that. We just announced that we're doing a partnership with Seagate on blockchain for that reason. We're gonna instrument our supply chain with blockchains that we can trace. I'm not going to have any more missing mainframes at JFK or wherever they are. It was actually Frankfurt. They had a strike and they chose to leave them out in the rain. They don't do too well in the rain. Oh, you just can't believe what happens in some of this stuff. It's all true, sad but true. Don't share that with anybody, even though there's a film here. What else?
Hi, I have a question. So other companies like Google have supercomputers and quantum computers. Is there a difference between yours and other companies?
Yeah, well, first of all, we are aware that Google has significant investment in quantum. They are, of course, not sharing a lot about their technology with us. So we don't really have obviously a clear understanding of the underlying technology. Our belief, though, is that their technology is not as accessible as ours is right now, because we have a computer that is accessible via the cloud by anyone that wants to use it. So we have not seen that same demonstration. Clearly, the technology that Microsoft is professing to follow is a different technology, the ions-based technology. And there's different points of view among quantum physics experts as to which one is best. We certainly have convictions that ours is the superconducting transmon is the right way to go, semiconductor technology. But there are different points of view. But we absolutely have an understanding of who's investing and where they are. I would say that Google definitely has a large cloud, doesn't have the same investment in these traditional high-performance computers that we have in terms of what I was talking about with Summit. The folks that have created those are obviously the Chinese today have about 47% of the world's supercomputing rank in that ranking in the total top 500. So different technologies used in those is, of course, a lot of Intel technology as well as Cray technology in some of these as well. The difference of what we did here is we created a new technology with a new processor that combines the GPU, the accelerating technology, to create an artificial intelligence-based computing platform. So, good questions.
Thank you so much. Very interesting talk. I've been for a long time wondering what the quantum computation look like. Right? I wonder if you can tell us like the mechanism of quantum computing in the kindergarten language, right? So for the modern computer, right, it's just a matter of sequence of bits of the binary numbers, right? And then the Turing machine pretty much can tell us the fundamental computation, right? That we read the bits, and then we do the bits, the operation, and then we can rewrite the bits, right? So that's how all this AI happens, right? Do you have any analogous story about
the quantum computer is still a Turing machine, right, in theory. But the way I think about it is because those qubits can be at different states, it's more of a probabilistic view is the way I think of it. So you look at the probabilities in some respects, and that's how you get the fundamental answer out of the machine. And it has these properties, as I said before, of amplifying the positives and de-amplifying the negatives in terms of how it should work with the right kind of error correction. But it's almost operating more on a probabilistic type of thought process in terms of the outcomes. And we've seen some of that in AI today, right, where we're operating on when it comes out of a recommendation for different inferencing or different models, what is the authenticity of the recommendation, how accurate is it, right? So that's what we're really closely monitoring here as we improve this notion of quantum volume. But there's a part of this, to be honest, that I believe only the quantum physics experts understand. And that's why we have people that can speak to them, and then we speak, we have an agile team where we all participate. And interesting enough, in the IBM team, we have quantum physics people who are more focused on the software stack. They live and breathe Qiskit, and we have some that live and breathe the hardware. And that is a great combination because both are absolutely important in this equation. Yes.
I'm back to his kindergarten time. I'm back to the gentleman's question on the make it a kindergarten level. I've looked and I've read and I still don't get it. I used to work for IBM for a long time. Jamie worked for me. So anyway, can you recommend any papers or anything that would get it down to a level that a pure Penn State engineer can understand?
Yeah, there's a lot of, actually on the websites that we provided out there, there's a lot of reference material that we have produced. So there is one video that one of our researchers wrote or did, Talia Gershon. I don't know if you've seen this, Stacy. This video out there has been watched over 1 million times, maybe more than that now, and she explains quantum to a 6-year-old girl, to a 13-year-old girl, and to a 20-year-old girl. And it's a nice little interview to really watch and say, because it starts to show the maturation of the process, as you explain it over and over again to these different age groups.
How do I find it?
It's on Twitter, I know. She's an interview. It's out on Twitter. Her name is Talia Gershon. But it's, maybe if you look for IBM Q, but we'll get it to the folks here to send it out, right? But it is one of the best ones, and of course she did it for a lot of different reasons. She's great at talking about quantum and explaining it, but also, once again, we're trying to get more of the ladies interested in this field, and so she uses the dialogues with the different ladies at different ages. I thought it was very interesting. But there's lots of references out there. I just find that some are more slanted to, particular domains of quantum. We also have some interviews that Scott Crowder has done. I'm not sure that I think Talia's is interesting because of the different age group dimensions, right? It is difficult, though. There's a leap of faith. There's the spooky aspect of it that Einstein described. It's still there, right, that makes it work. But we can see it in action, particularly as our machines have evolved into these different levels of fidelity. In fact, we see a marked difference between the machines already, and we've been in research here for decades. I remember the first time I went to IBM Research to start working on quantum, which was about 2 years ago for us as a product team, and one of the guys looked at me and he said, "Yeah, I've been working on this for 25 years. I'm the lead quantum physics guy on this team here." And of course, Charlie has been working with IBM. I think I calculated he's 76. I don't know if I've got that quite right. But it's decades of investment sometimes to create something like this, to really keep investing in the notion that you will find a commercial use for it, right? Okay. If there's any other questions?
Hi.
Somewhere.
Hello. Over here.
Over here.
Hi. It's great to see another woman up here who has been pioneering the industry as much as I have for many years. So thank you for everything you're doing, Jamie. So to help out, I have problems too growing into what the new computers are doing. I've watched everything from step switches to digital multiplex switches to fiber. And, you know, as we keep growing, I think as we get older, our minds get harder to see what's evolving. Perhaps maybe some classes, or maybe even get you on TV and talking to the public and the consumers on how we can use this. I think that's the biggest thing is how are we going to use this? And you know, we see a lot of uses in the financial industry, the medical industry. I'm looking for cybersecurity answers. You know, what are we doing inside the quantum computer to address some of those security measures that we didn't address when we, you know, leaped into artificial intelligence and the cloud. I don't even know what Google is doing in that area. I have spoke with them. But it would be nice to see IBM kind of come outward a little bit more. When you had Watson, you know, we saw Jeopardy. I think that was the last time we saw a face of what IBM is doing. And I think maybe you need to come out a little bit more and help us see what more we can do to interface with it as users, consumers, engineers, in our future.
Yeah, well, I think that that's a great comment, and clearly it's important that we do these kinds of events to share where we are right now. I think that we're very much at the beginning of commercial proof points, and as we understand more about those commercial proof points, we will definitely share our perspective of what's achievable in partnership with our partners. You can imagine that some of those partners up there are fairly secretive about what they're doing. We see a difference in them in terms of who shows up at the table with quantum physics people on their staff, which they do. But you can imagine that some of them want an advantage with what they actually determine, and that's part of our intellectual property contract as well, is that if we understand something from the process that advantages our machine, we have rights to it. But of course, they have intellectual property rights to everything they create for their business and their domain, including their algorithms. So, you know, I think we'll find that balance. You know, we have visions of these big solutions that we can start to share more about. And one of the things that we did feel like we learned from Watson is that we don't want to overpromise before we fundamentally understand things, but we also want to make sure that we convey that we IBM are in this game. We believe we're ahead right now and not these other guys, but we want to be clear about what we think is doable today and what's not. But you're right, we have to strike that balance, right? Because if we don't get out there and share enough, then most of you won't know what we're doing at all, right?
Well, thank you for picking NC State.
Well, they helped, we worked together for a mutual selection, but I would have to say that NC State, you know, moved fast. NC State moved fast, and I think that's a testimony to the university and also to our area, to our region. You know, we're serious about technology. It's not all about Silicon Valley, and our houses are cheaper here. I went to Grace Hopper, you know, to recruit women. There were 22,000 women there, and some of them were really excited about the housing prices in this area. So it's funny. Okay. Good comment.
Give it to this young lady right here, and then anyone who has a question afterwards, you'll still have time at the reception.
Yeah, we got ambassadors here too that are trained, or so they told me.
Hi, thank you very much for speaking tonight. So I actually attended a talk on quantum computing and artificial intelligence about 2 weeks ago to the Department of Humanities and Social Sciences, and they were talking a lot about the security implications of AI. You mentioned that China, there was definitely a big push, and they had 47% of quantum computing. How is that working with research and development? Is there more of a national effort with the U.S. like China's having, or in the U.S. is it more privatized?
So that's a very good question. First of all, the 47% is the number of supercomputers they have on the top 500. So those are traditional supercomputers. But clearly, yeah, that's evidence that China is very serious about investment in IT technology, as many large countries are, by the way. So I think that the U.S. has certainly, you know, like all other countries, you see a wide variety of geographies on those hubs, whether it's Japan or Germany or etc., understand that this is important for the future of computing, and that if you want to have control of your own destiny in terms of commercial value and also security reasons, you definitely have to invest here, right? So the top 500, though, I think, is something that a lot of maybe folks lost track of for a while, because we don't necessarily understand the value of some of these supercomputers and what they can do. Quantum is just the next evolution of what could be done in the future. But that's a great question. It is definitely viewed as a commercial and national security topic. And of course, the governments will never tell us what they're doing, including the U.S. government. I mean, you know what I mean? The average person would not know what's going on, right? Because they look at it that way. But that's why they're all investing billions in this. We believe there's billions of investment by governments in this. So,
Thank you, Jamie.
yeah. Thank you. Thank you, guys.